I am going to go ahead and begin the broadcast now. Thank you, everyone. Thanks for joining this webinar today. This is a webinar on introduction to Apache Apex and a comparison of Apache Apex with the traditional streaming system, as it were, which is Apache Storm. I am Devendra, and I work with DataTorrent. I'm also a committer on Apache Apex. A brief introduction about Apache Apex. So Apache Apex is a platform and a runtime engine which basically enables development of scalable and fault-tolerant distributed applications. Now, this is a lot of jargon, I know, but in reality, what it means is that you're able to write your business logic and run that in a distributed environment on top of Hadoop to do parallel data processing at massive scale in a really low latency sort of a fashion. Apache Apex is Hadoop native, which basically means that we leverage a lot of yarn functionality to schedule the streaming containers and to run your applications in a distributed fashion. This works on the process of streaming. So Apache Apex is based on the concept that streaming is really a superset of batch and not the other way around, which is getting sort of traction with Apache Spark, where they say that stream is essentially an unbounded batch. Apache Apex and Flink and Storm sort of rely on the concept that batch is just a special case of streaming, or a subset of streaming, as it were. It's extremely high throughput and low latency because the downstream operators don't wait for any batches to be completed in the upstream. It's an event-by-event processing system. Apache Apex, along with giving the core platform functionality, also offers a range of commonly used operators packaged together under Malhar, which is the library that sits on top of the core engine. Typically, the users would end up writing only business logic alongside these operators to make their distributed application work. Nothing else is expected out of business users. All the platform guarantees will stay as is, because this is just a library that will sit on top of Apex core. Moving on. Coming to the applications on Apex. Apex gives you distributed data processing. Sorry. Guys, can you see my screen moving? Can someone just ping me if they can see the latest screen? It should read applications on Apex. Oh, it's stuck. All right. Give me a second. All right. Let's try this. Okay, guys, moving now. Can someone please ping? It should be on applications on Apex. Oh, all right. Give me a second, guys. Is it moving now? Oh. I'm trying to fix it. Give me a second. Okay, I think it should be fine now. Great. Sorry for the interruption. Apologies. Coming back to applications on Apex, so you can run your distributed application on Apex by using these assembly blocks called operators in the nomenclature. These the operator interface is pretty straightforward, and it follows a specific life cycle. And all the user is expected to do is basically write his or her logical code into the operator, and then the operators can be assembled in a seamless fashion using the Stream APIs that are provided with Apache Apex. Apache Apex supports distributed processing of these logical blocks, and the entire orchestration is done with the scheduling is done with the help of Yarn, and the orchestration is done with the help of a streaming application master, which is a concept native to Apache Apex. Operators can be scaled up and down at runtime. For example, you start off your application with 5 operators with 1 instance of each of the operators. Over a period of time, you realize that you need multiple instances of the same operator, and then you need to scale up and down. Now, this can be done with Apache Apex based on user-defined SLAs. For example, if your Kafka throughput needs to be 10,000 events per second, and the number of operators corresponding to that is 10, and the throughput drops, you can basically cut down the number of operators you have, or you can scale it up to double the operators you have. There's no limit that it goes into an exponential backoff. You can do it at user as per the user SLA. Fault tolerance, Apex actually supports application-wide state, and automatic recovery from node outages is provided out of the box. So what that basically means is that at any given point in time, you don't have to replay state from the start when your application basically started. You replay the most recently checkpointed state at any given time. This is incredibly useful in longer running applications because state tends to build up over a period of time, and then you will spend a lot of cycles replaying the state if it's not checkpointed appropriately and if it's not replayed from the last checkpoint only. Like I said, operators is the basic building block of Apex. There's a library that gives you a nice a bunch of operators which are pre-built and hardened, which is Apache Apex Malhar library. In addition to that, writing an operator is pretty easy using the operator interface. There's a Java API provided for it. Some support is available in Scala too. And actually a declarative API has been released as a part of the 3.5.0 release recently, which basically lets data scientists assemble the operators pretty easily. In addition to this, DataTorrent as a company gives up a bunch of convenience tools for operational insights. These are basically UI and drag and drop layers and debugging tools that sit on top of Apache Apex to help speed up deployments and let a user debug something in production directly. Coming back to the Apex stack overview, actually, before this, I'll just take a few questions if there are any. All right, no questions yet. Great. Okay. Moving on. Let's take a look at the Apex stack overview. So Apex as an engine has only one prerequisite, which is Hadoop 2.0 and Yarn. It needs Yarn because it's native to Yarn, uses Yarn for scheduling containers and other orchestration across the cluster. Now, Apex can run on a physical server or a virtual machine. It can run on cloud or off cloud in AWS, Azure, what have you. On top of this, like I said, the only thing that Apex really needs is Hadoop and Yarn. So anything in the Hadoop ecosystem and up is supported, is all it needs. Apex is certified against all major Hadoop distros, Cloudera, Hortonworks, Pivotal, and Napar. All have certified Apex, and it runs seamlessly on any of these distributions, both on physical as well as VMs and on cloud, off cloud as well. On top of this sits the Apex core engine, which essentially gives you the streaming runtime with very strong performance guarantees, fault tolerance guarantees, and it supports complex in-memory data processing for streaming data. Again, all of this is provided out of the box with the Apex core engine. On top of this, you have an open source library of operators called Malhar, and a lot of convenience operators are provided here, basically to connect to commonly used systems like JDBC in and outs, or Kafka in and outs, JMS in and outs, file system in and outs, etc. Your streaming application would essentially operate at this layer. It would leverage the Apache core. It would use the operators from Malhar and your own custom operators, leverage Apache Apex core, and then run on top, run in a distributed way on Hadoop using Yarn as the scheduler. On top of this, DataTorrent as a company gives you graphical application designer and launcher, drag and drop tool to assemble applications and to run them. Additionally, there is a data visualization dashboard that gives you visualization into the in-memory events, and other operational metrics are also published with it. Management console, again, is a convenience tool to give you an overview of what's happening in your application from an operations perspective. There's also a REST API layer that can be leveraged by Apex users to interact with the running application or to submit applications. Moving on, I'm just I'm just going on to the next set of things, which is the Malhar operator library. Now, operators in Malhar are broadly categorized in terms of the usage patterns. A typical application that you would see would have one or more input adapters, one or more output adapters, and a bunch of operators connecting input to output. So what we have done here is a lot of convenience operators are provided with Malhar. In the input and output space, you have connectors to the prominent file systems, S3, HDFS, any local file system essentially, and network-mounted file systems. In the RDBMS space, we have connectors to PostgreSQL, MySQL, and a few others. In the NoSQL space, there is Hive, Edgebase, and in the messaging space, we do support GMS messaging. In addition to this, in terms of the queues, we have very strong connectors to Kafka and Kinesis, which are the message buses of choice for streaming systems. And this is both in and out. So yeah, in terms of the compute operators, there are out-of-the-box operators for pattern matching, machine learning, and algorithms. There's a Samoa integration, which is in a good shape now, and a calcite integration as well going on. There are a bunch of parsers provided out of the box. These include a CSV parser, a JSON parser, which is based on Jackson, streaming JSON parser, and XML parsers provided out of the box with Apex. Moving on, when I mention native Hadoop integration, what does that really mean, right? So in the Yarn world, so Yarn is the resource manager that packs with Hadoop 2.0 and up. In the Yarn world, you have a resource manager, then there is a per node manager, which basically takes care of whatever happens on the node in terms of the processing. It governs the Yarn childs running on the node essentially. And then there is an application master, which is like the master of the application, taking care of negotiating resources with the resource manager and receiving heartbeats from individual containers that are a part of that application. Here, HDFS is used for storing any persistent state. Now let's take a deeper dive of what's actually happening in this diagram. So essentially, when you run a streaming application, it would be distributed across different nodes, and it would be multi-tenant, as in one Hadoop cluster could have different applications. They may or may not be streaming applications. So here, here an Apex application is shown in these green boxes, and a MapReduce job running in parallel with it in a multi-tenant way is shown in these pink boxes. Node managers exist on each of these nodes. Here I have an Apex application running with 6 containers, 6 operators, and they are spread across 1, 2, 3, 4, 5 containers, and Stram is the additional 6th container governing everything. Each of the containers relay their heartbeats to Stram. Stram basically takes a logical plan, converts it into a physical plan, procures the resources to run those containers from the resource manager, and then actually spawns that application and takes care of heartbeat protocol. So every operator relays a heartbeat back to Stram. If an operator goes down, Stram basically negotiates more resources with the resource manager and respawns that application. The data in this application is flowing from operator 1 to operator 3. Operator 2 is also an input adapter relaying data to operator 3, and then operator 3 is giving it back to 5 and operator 4, and then it's getting out from operator 6. Now here, there are multiple concepts going on in terms of the locality. Now, operator 1 is on its own spawned in a different node than operator 2. The Stram and operator 2 are what you say node local. Operator 3 and 5 are again node local. Operator 4 and 6 are container local. Moving on to the next one, I'm just seeing if any questions are there. Okay, I'm going to take a few questions if they have not been answered. Could you show full screen? I'm actually having trouble showing full screen, I'm sorry. I'm not sure if it supports Linux audio. I don't think it does. What is the difference between Apache Storm? Yeah, I'm coming to that, Tola. Give me a minute. Yes, applications and processes are monitored. DD Gateway is basically a convenience tool provided that sits by DataTorrent as a company that sits on top of Apache Apex. It uses a REST API, which is in the open source, to basically see how to spawn applications, see operational metrics around the applications, and to kill any operators or to change the topologies or properties of an operator. Does it support Python, Node.js? Yes, it supports Python. There's a script operator that you can use in which you can write Python code, and it's supported. Node.js and C++ language. I think there is a C integration at some point, but wouldn't really go to the extent of saying it's supported. Node.js, I don't think so. All right, guys, moving on. Let's see how the application development model for Apache Apex looks. So Apache Apex follows a DAG-based model, which is a directed acyclical graph. Essentially, what you need to do is the nodes are operators, in which your business logic or your the logic that you want to implement really goes into, and the edges are essentially stream of tuples which connect to operators. So here in this diagram, you see operators in blue. They're shown with an ellipsis format to basically demonstrate that there can be multiple instances of these. A stream is essentially a sequence of tuples that flows between two operators. An operator would take in one or more streams, perform computations on it, and emit one or more streams out of it. An operator can have multiple instances that run in parallel with each other, and there's no prerequisite or there is no constraint on a tier of operators to have a specific number of operators. For example, you could have 3 instances of an operator here and 7 instances of an operator here, and all the orchestration is taken care of by Apache Apex internally. Okay, moving on to windowing support. There's a lot going on in this diagram, but I'm going to try my best to explain a lot of it. So the tuples that you see in white are your data tuples flowing through, and essentially Apache Apex has some control tuples, which are begin window tuple, end window tuple, and a checkpoint tuple. What happens when a data tuple flows between an upstream operator and downstream operator is that periodically the platform would insert a begin window tuple and an end window tuple, and all the state management happens between a begin window tuple and an end window tuple. Periodically, the platform would insert a checkpoint tuple. When all the operators in a directed acyclical graph receive a checkpoint tuple, they snapshot their entire state initially to the local disk, and then there is a asynchronous daemon that copies all that state from the local disk to HDFS. Now, Apache Apex supports two types of windows inherently, which is sliding window and tumbling window. Sliding window is basically has a length and a slide interval. So basically, in this case, a sliding windows would have some overlapping tuples between two windows. Tumbling window essentially is fixed. It starts after a specific time period, goes on for a period, and then the next window is started. Like you can see, Apache Apex is introducing no artificial latency because begin and end window tuples are only control tuples that are inserted amongst your data tuples, and the downstream operator would not wait for an upstream operator's end window to be triggered before processing the data. Once a data is relayed out of an upstream operator, it goes to a downstream operator. These tuples are inserted only for checkpointing purposes. They don't add any latency whatsoever. Think of streaming like a continuous assembly line. You're not stopping the assembly line at any given point in time. Okay. Recently, with windowed operators, Apache Apex has introduced support for session windows and event time windows as well. So that's covered too. Quickly going to stop for a few questions. Yes, the slides will be available, Joydeep. Can operators scale out be automated? Yes, there is a concept associated with that, Samuel. I'm coming to it in one of the later slides. What's the purpose of three specific tuples begin and end? Can you please give an example? Yes, I will also discuss application security at a later point. Yeah. So begin and end window is essentially used to categorize tuples so that checkpointing can be done between a begin and an end window. There is also a concept of a partial window. Yeah, I'll come to that at a later point. You don't want to checkpoint or acknowledge one tuple at a time. Essentially, what you do between a begin and an end window is let's say window 1, 2, 3, all the tuples went through, and you had a failure between when you're processing window 4. Now you know you don't want to replay anything from window 1, 2, 3. So essentially what you would end up replaying is the partial window 4. So for this, Apex actually uses a windowing concept, and begin window and end window tuples essentially give you the start and end of it. So yeah, stateful recovery from the previously checkpointed state is what you would typically use Windows for. Let's take a look at an application written with Apache Apex using the Java Compositional API. Here I'm taking a very simple example, which is a commonly used one, the hello world of big data world, of big data space. You have an input, let's say it's a file input. I'm reading one line after the other from the input. I'm parsing the line based on spaces and some special punctuation marks, emitting words out of it, counting the words, and emitting those counts on a console. All you have to do for writing an application is implement the streaming application interface and override the populate DAG method. Here what I'm doing is I'm having a line reader operator, which is coming from Malhar. I'm adding it to the DAG object, which basically assembles a directed acyclical graph. I'm calling that operator input, which is the same name as here, and I'm creating a new instance of that. The next operator that I have is a parser. I'm adding the parser to the DAG, creating an instance. Then I have a unique counter pulled in and a console output operator. Correlating this to a directed acyclical graph, what I have added till this point, line 4 in this function, are essentially the nodes of a graph. Now I need to join them. So I say, okay, I'm adding a stream. I'm calling it lines, the same name as above. And what I say essentially is the output port of the input operator should send data to the input port of the downstream of the output operator or the downstream operator. So an upstream operator's input port, output port is going to relay data to a downstream operator's input port. The way I assemble this stream would be I'm calling it lines. line reader or output is parser.input. So line reader has a port called output and parser has a port called input. I'm just putting them together using the stream interface. Then I go on to say, okay, words parser.out goes to counter data, and then counts is another stream in which counter.count, which is an output port on the counter operator, is giving input to the console input operator. Let's take a deeper dive into how easy it is to write your own class or your own operator, really. I'm saying parser is my own custom operator. Going back to the previous slide, you can see that parser was one of the intermediate operators here. I'm saying, okay, parser is my own operator. I just need to extend the base operator. This particular operator has an input port. There's a default input port interface implementation given in Malar already. So you can just override the process method in that, and say here I'm splitting an incoming string using some punctuation marks and a white space, and I'm emitting it on the output port. Like you can see, the output port is declared here. Going back to the previous slide, you would see that line reader's output is going to parser's input, and parser's output is going to counter's data port, which is really the input port. Let's take a deeper dive into how a counter looks. Here I've implemented a unique counter. There's a default input port which takes a key, which uses a key value pair. The key is essentially the tuples coming in or the words coming in, and I'm maintaining a unique counter of it. At every end window, I'm emitting a key value pair of the map. As you can see, I'm not resetting the map, so the counts are essentially cumulative. Quickly going to take a few questions, if there are any. Are computations frozen during checkpoint? Yes, checkpoint is a blocking call per se. So when an operator receives a checkpoint tuple, it stops what it's processing and until the checkpoint operation is done. But because it's a local checkpoint on the local file system, it's pretty quick and efficient. Yes, we'll share the recording. Can you have window based on size or time? Window based on size? No. Window is based on time in Apache Apex, not really on size. Yeah. Okay, moving on. Let's take a closer look at partitioning and the concept of unification. When you assemble your DAG at a logical level would look something like this. For example, I have a DAG in which I'm reading from Kafka. I am parsing the records that I'm getting, and I am enriching them and then aggregating them and writing to an output. So this is a 5-stage DAG. For the time being, let's say I'm only reading from Kafka, parsing, and using a console output operator. I'm going to represent those 3 operators by 0, 1, and 2. So my logical diagram or logical DAG would look something like this. Operator 0, 0's output port goes into 1's input. Operator 1's output port goes into 2's input. When I run this DAG using Apache Apex in a distributed fashion, what would happen is that I may have 1 or more instances of any of these operators. In this particular case, I have 1 instance of operator 0 and 3 instances of operator 1, which are going into 1 instance of operator 2. Now you have to unify the output of multiple instances of operator 1 before they go into operator 2. That's where the concept of unifier comes in. At a very high level, think of unifier like a combiner in the MapReduce world, where it's receiving data from multiple map jobs, running, combining that, and sending it to a reducer. Combiner is local to the node where your mapper is running. Here, the unifier may be on the same node or on a different node, but the salient feature of Apache Apex is that it will insert the unifier for you, so you don't have to worry about bottlenecks between upstream and downstream operators. Apache Apex supports multiple ways of partitioning. You have n-cross-m partitioning scheme or a parallel partitioning scheme. In n-cross-m partitioning scheme, what essentially happens is that you may have n instances of an upstream operator talking to m instances of downstream operators. So I may have 4 instances of a Kafka input operator talking to 16 instances of a CSV parser. Here I'm taking a logical DAG again. I have operators 0 through 3. What's happening when I convert this into a physical DAG in this particular diagram is I have 1 instance of operator 0 and 3 of operator 1, A, B, and C. Then I have a unifier that's combining the output of operator 1 before it goes into operator 2, and then I have another unifier of which combines the output of operator 2 before it goes into operator 3. Over a period of time, there could be a bottleneck between operators 1 and 2 and 2 and 3 as well. So Apache Apex supports a concept of cascading unifiers or multi-tiered unifiers as well. So what's happening is Apache Apex would insert another unifier in parallel to the unifier that you already have, and data from disjoint data from 1A and 1B and 1C would go to unifiers. None of the data would be duplicated between unifier blue and unifier green, because there's a concept of stream codec and hash and a hash-based mask to basically see that only a subset of the data is going to a disjoint subset of the data is going from an upstream operator to a downstream operator. A DAG, I'm going to take a question here. A DAG is a directed acyclical graph. It's a processing paradigm used in distributed computing world. Yes, I think I have taken this one already. I'll go on. Okay, now continuing on advanced partitioning. Parallel partitioning scheme is another scheme in which if you have n instances of an upstream operator, you would have n instances of a downstream operator. If your logical DAG looks something like this, you have operators 0 through 4, and your physical DAG is looking something like this, wherein you have multiple instances of operator 1A, which is 1A and 1B, and then the input is being unified before it goes to operators 2, 3, and 4. This unification bottleneck could be solved multiple ways. You could have a cascading unifier, or the better way to do it is having parallel partitioning scheme, wherein if you say that operators 1 and 2 are in a parallel partitioning scheme, then the same number of instances of operator 2 are spawned as the number of instances of operator 1, and then operator 2 and 3 again are in a parallel partitioning scheme, so same number of 3 instances of operator 3 are spawned as operator 1. The output of operator 3 is unified before it goes into 4. There's a notion of cascading unifiers which Apache Apex supports. This is to overcome any network interface bottlenecks that you may see, or any unification bottlenecks as well. In this diagram, unifier red is becoming a bottleneck because all the output from 1A and 1B is flowing into it. Apex actually has gone on a step ahead and eliminated this using a cascading unifier approach. In this particular case, I have my 4 upstream operators pushing all of the data to a downstream operator, which is in a different node, a different rack even. So all the data is flowing through a network interface card, and my unifier is actually located beyond the network interface card. Apex would basically spawn unifiers for operators being on the same rack or the same node, backed by the same network interface card. Apex would introduce a unifier that is again going through another NIC and another NIC into the final downstream unifier. In this way, the unification bottlenecks can be eliminated using a cascading hierarchy of unifiers. I'm going to stop for questions after this. Let's take a look at dynamic partitioning, right? Like I said earlier, you could start off your application with 5 instances of every operator. Over a period of time, you may realize that you need more instances of it. For example, you have a parser, which is of which you have 5 instances. You're reading data from Kafka, then you have a parser. Over a period of time, you may realize that the throughput that Kafka is giving has reduced, because of which your SLA is getting affected. Now, you may up your Kafka input operator based on the number of tuples, based on some latency metrics that you are having, or basically number of tuples that you are able to process throughout your DAG in a given period of time. For this, Apex gives you an ability to have dynamic partitioning changes. Partitioning is triggered based on the SLA given here. This is done while the application is running and it's stateful. So you have a notion of initial number of partitions that can go up and down based on some throughput numbers or a user-defined SLA. State is redistributed, and you have an API for custom partitioning provided by Apex natively. In this case, we initially start with 2 instances each of operators 1 and 2, going into 1 instance of operator 3. Over a period of time, operator 2 scales out, and over a period of time, operator 3 scales out. In this particular diagram, we're not showing any unifiers because they may just clutter the diagram. Quick question time. Okay, if checkpoints are local to a node, then is the distributed state checkpoint consistent? Yes, it is consistent because only the writes of checkpoints are happening locally. They're actually copied over to HDFS asynchronously. How do we determine how many of the same operator are needed? Well, actually, that's up to the user how many instances he needs based on domain knowledge. But what you can do is if you're implementing the custom partitioners, then you can scale up and down as need be based on your throughput SLAs. Will Apache create an operator on each node? Well, Apache doesn't really create any, or Apache Apex doesn't really create any operators on each node. That's the responsibility of Yarn, which is used for resource negotiation and scheduling. So yeah, but there are guarantees that Apache Apex gives. There's a concept of affinity, which basically gives you the ability to pack 2 operators on the same node. There is also a concept of locality that Apache Apex gives you, which basically means, let's say you have 2 operators, a Kafka input operator and a parser. You could say that they have to be container local or thread local or node local, and those kind of guarantees are honored. Is partitioning automatically selected by Apex, or you have the option to configure partitioning? Yeah. On which date/time windows can we define processing time Kafka offset? Yeah, event time window, processing time windows are natively supported, but there is ability to do event time windowing also using the windowed operators. I don't get this question. What is the ordering casual model for tuples across distributed system? I don't understand this question. Okay. Now let's take a look at how tuples are actually partitioned across the system, right? For example, if you have an input upstream operator, 4 instances of it talking to 8 instances of a downstream operator, how do you make sure that disjoint subsets of data are actually flowing through the system? Every tuple in the Apache Apex terminology has hash code, and there's a concept of a mask that's used by downstream operators to uniquely identify which parts of tuples coming from the upstream operator they need to consume. So for example, I have a tuple with multiple fields in it. I have a name, some pin code, and an address. Stream codec is basically used to specify custom hash codes on tuples. In this particular case, I have a tuple which is translating to this particular hash code. Then downstream operator would basically apply a mask on it. In this case, I'm using an AND mask, and I have 4 partitions of the downstream operator. So this particular tuple would be consumed by partition 2 because that's the mask that's giving it an AND of 0, 1. The users can write their own stream codecs using the stream codec interface, and special serialization or specific serialization can also be provided using the same. The hash code method can be overridden to pick what you want to. Custom. Okay, in this particular case, I'm showcasing a broadcast example. So this is another example of custom partitioning. Here the mask is AND with a 0, so whatever the upstream operator is emitting is going to all of the downstream operators. Let's take a look at the fault tolerance concepts of Apex. So once a control tuple, like I said before, once a control checkpoint tuple is received by a particular operator, the operator halts and checkpoints its entire state and then moves on. In the checkpointed state, all non-transient variables inside the operator are actually checkpointed. If you don't want to checkpoint something, mark it as as transient, and it won't be checkpointed. Operator checkpointing is automatically performed by the engine. The user doesn't need to write any code for this. In case of a failure, operators are actually replayed from the checkpointed state, and all the windows from that point on are replayed. The frequency of with which you want to trigger a checkpoint is configurable. The checkpoints happen initially to the local file system, and then they're asynchronously moved to HDFS to give a unified view, as well as give the user the ability to checkpoint a lot of state. Default storage HDFS, but checkpoint is really an interface. So you can, there's an implementation for geode, which is an in-memory data grid available with Malhar, but essentially you can checkpoint state to any store that you want. Apache Apex does automatic detection and recovery of failed operators using a heartbeat mechanism. This is orchestrated by the STRAM. So if the STRAM detects that a particular operator has not sent it any heartbeat for 30 seconds, that's a default, again configurable, then it basically goes on and respawns that operator. There's a buffering mechanism to ensure replay of data from a recovery point. So there is no, essentially no loss of data. It's orchestrated using a concept called a buffer server. The state of the application master is checkpointed, and two application master failures are actually, if application master fails, then it's restarted from the checkpointed state twice. That's a yarn level guarantee again. And now let's take a look at buffer server. Buffer server is what Apex uses for handling for replaying tuples from a committed state in case of failures, as well as handling back pressure. Think of buffer server like a in-memory Kafka. It supports a in-memory publisher subscriber mechanism. A buffer server essentially sits alongside the output port of an upstream operator. Here you have one operator in node 1 and one operator in node 2 in each of their containers. So the upstream operator, operator 1, would have a buffer server connected to its output port, and the downstream operator, operator 2, would be consuming from that buffer server. Like I said, buffer server is follows a publisher subscriber mechanism. The publisher to the buffer server is operator R1, and the subscriber to the buffer server is operator R2. Before a data is actually committed, it's stored in the buffer server. So operator R1 essentially would write all the data to buffer server, and operator R2, operator 2 would consume data from that buffer server until a committed callback happens. The data is pushed from a buffer server only at a committed callback, and not before that. A committed callback is essentially state that represents that a tuple has flowed from across the DAG all the way up to the last operator in the DAG, and every operator has actually committed the window under which that tuple was falling, and now you don't really need the state for that operator, and it can be purged. Okay, I'm going to take a few questions. How will node 1 buffer server know how to route the output to node 2 operator? Okay, I think it's a great question. So the way the downstream, so we just saw the stream codec and the hash concept earlier, right? So every downstream operator would subscribe to a buffer server of an upstream operator, but it only ends up picking up what it needs to based on the hash and the mask logic that we saw earlier. So it's not like a relay broadcast mechanism that's followed. Let's take a look at the recovery scenarios for Apex. Suppose I have a bunch of windows flowing through my DAG. Here I have end window 2 being called, and then I have two tuples, two tuples which have 1 and 3 inside of them, just a number. Then I have a begin window being kicked in, and then subsequent windows flowing. Let's say at the end of the second window, my sum is 7, and now I have an operator failure. Now, what you really want to achieve is start from 7 and not from the previous, not replay all the tuples until you come to 1 and 3. Now, after my sum was 7, let's say I got a few tuples which, let's say I failed at a and I got subsequent tuples. What happens is that the sum 7 would be checkpointed, and the subsequent tuples, which are 1 and 3, which are 4, 2, and 1, would be which are 1 and 3, would be stored in the buffer server. Now, when the failed operator comes back up, what happens is that you have the recovery state of the sum variable, which is at 7, and then the subsequent tuples are replayed. So essentially, I would replay the tuple 3 because tuple 1 and 3 from the buffer servers and apply the same counts on it again. So my base count would be 7, and the buffer server would replay tuples 1 and 3, and then I would add 4 more to 7 and achieve 11. Let's take a look at the processing guarantees. So Apex supports at least once, exactly once, and at most once. At least once is usually good for most cases. On recovery, data is replayed from previous checkpointed states. Messages will not be lost. All the partial windows would be replayed. This is the default mechanism, and it's usually suitable for most applications. At most once is another semantic. On recovery, the latest data is made available to the operator. It's useful in cases where some loss is acceptable, and in exactly once mode, you can actually achieve exactly once with at least once semantics and some state recovery logic. So at least once with idempotency means exactly once. On the input and the output adapter side, you would need idempotency. Definitely, all the intermediate operators are idempotent anyway. Some user code is essential for this though, because input and output adapters are special adapters, and a lot of their behavior depends on external systems. For example, if you're consuming from Kafka, you can achieve exactly once because Kafka has a notion of offsets. The same may not be true for a few of the other systems where you don't have a strong notion of granular offsets. Stream locality is the ability. By default, operators are deployed in containers, and they're deployed randomly across different Hadoop nodes, but you can actually specify how two operators should be located. That brings us to the concept of stream locality. So four types of locality are supported out of the box with Apex. There's rack local, node local, container local, and thread local. Rack local means data does not traverse network switches. Node local means data is passed via a loopback interface and doesn't go over the NIC, the network interface card. Container local means messages are passed via memory queues, and no serialization of data is required. And thread local is a concept that is pretty unique to Apache Apex, wherein messages are passed between operators as if they were subsequent function calls. So essentially, the functionality of two operators and the messages flowing between them is the same as functions being executed from a call stack. Okay, I'm just going to take a couple of questions. Quick time check, guys. Why hash code based? Why not simple? Yeah, actually, round robin based balancing is also available. You can leverage that, but hash code based is the default one. A binary hash code is used essentially. Let's take a look at the most commonly used case that we see. You're reading some web server logs, putting them into Kafka, and then you have a bunch of operators, which is a Kafka input operator to read those logs. Then you decompress, parse, and filter, and you do some aggregation on it, and you may be using a Kafka-based pub/sub to write and visualize it. This is one of the more prominent use case. The reason I'm bringing it up right now is I'll refer to this use case when I explain the differences between Storm and Apex. Let's take a look at what native streaming really means, right? When you say event by event processing, what it essentially means. So here you are getting a stream of data into the input operator. The input operator is not buffering that data at all. It's doing reading that data and passing it to the next operator. The next operator is again processing that data, sending it to the next one, and so on and so forth. In a micro batch system, if you will, what happens is that the upstream operator receives a batch of data, keeps it buffered till a particular time, and then sends it to the next one. Now this introduces inherent latency, but in a native streaming system, there's no latency because a tuple is being relayed from an upstream operator to a downstream operator as soon as the upstream operator receives it. Think of this as an assembly line, wherein one person is assembling part one and sending it to putting it back on the assembly line as soon as he's done assembling that part, and the next guy receives it. Let's take a quick look at some of the key concepts of Storm. So Storm has a daemon called Nimbus, which is a master node responsible for distributing data among all worker nodes. Its task is to assign partitions, assign tasks to worker nodes, and monitor their failures. It's like a supervisory daemon that governs everything. A supervisor is what runs a worker process and governs worker processes to complete the task assigned to them by Nimbus. A topology is pretty similar to a DAG. It's essentially the logic for a real-time application that runs on top of Storm. It's essentially a directed graph of spouts and bolts and the interconnections with stream groupings. Stream grouping is a concept that's pretty similar to a stream. A stream is basically a core abstraction of Storm. It's an unbounded sequence of tuples that is processed and created in a parallel distributed way, very similar to the stream concept in Apache Apex. The concept of stream groupings is pretty similar to the stream codec concept in Apache Apex. A spout is essentially a source of streams in a topology. This concept is similar to an input adapter in Apache Apex. Spout in Storm terminology is the entry point into your topology. Then bolts are essentially intermediate operators like in Apache Apex. They do filtering, aggregations, joins, or any user-defined code. Now Zookeeper is essentially the supervisor that's used to interact with Nimbus. It's responsible to maintain the state of Nimbus and the supervisor, along with keeping a track of shared data between different bolts in Storm. Let's take a quick look at Storm parallelism. The basic unit that Storm gives is a worker process. So you could, when you spawn a topology, you would essentially spawn worker processes, and the worker processes would have executors inside of them, which are essentially threads running tasks. And a task is what would run a spout and a bolt. Here I have two worker processes, and I have said that my yellow bolt has a parallelism of 6. So you will see 6 tasks there, and my green bolt has a parallelism of 2, but the executor there has a parallelism of 2 as well. So I would have 2 executors with 2 tasks each here. And I'm saying my blue spout has a parallelism of 2, so I'm saying 2 tasks here. Quick time check, guys, getting to the end of it. I'm going to take a couple of questions before I move on to this slide, though. I don't see any new ones. All right, going to go ahead. Let's take a quick look at the architecture and features of Storm versus Apex. The processing model between Apache Apex and Storm is pretty similar. Native Storm is native streaming, and the Storm has a high-level API which works on micro-batch concept with very strong guarantees. It's called Triant, that works on micro-batch, so that's more latent. Apache Apex, again, is native streaming in memory computation with very strong guarantees for data in motion. In terms of the language support, Storm is essentially written in Clojure, but they do have Java-based APIs and ability to use non-JVM languages. Apex is written in Java and has a decent Scala support. In terms of the API, Apache Apex Storm supports a compositional API,
Native Storm is compositional API, and Triant is declarative API, high-level API, very suited for rapid prototyping and data scientist kind of use cases. They have SQL support available via Triant, although albeit it's limited. Apex has a compositional DAG-based API. Declarative API has been released with 3.5.0 released recently. It's emerging, but it's already there for use. Locality. When we say locality, it's the locality of data where it is. Storm really doesn't give the user the ability to co-locate to executors or to tasks on a particular node. Its integration with resource managers is pretty reasonable. Apex, on the other hand, gives node locals, rack local, container local, and thread local options. So you can actually pack two operators doing similar computations or complementary computations with these options that you have. Latency, Storm is low latent, has low latency by default. With Triant, the style is micro batch, so you would have a higher latency there. Apex scales horizontally really well, and it is really low latent. Millisecond latency is supported by Apex. Throughput. So Storm gives you multiple modes of running. You could run Storm in an acknowledgement-based mode or a no-act mode. The throughput of Storm in no-act mode is pretty good, but it could be lossy, as in without an acknowledgement from downstream executors, downstream boards or to the spouts, you would end up losing data in your application, which is usually not desirable. In this particular case, the throughput is pretty limited. Apex gives very strong guarantees. At least once is supported inherently, so even with that mode, it gives very high throughput. Scalability, again, if you're using acknowledgement-based mechanism, Storm has this concept of ACK trees. So any tuple coming into the system by a spout is marked with a unique ID, and that ID is at the root of an acknowledgement tree, and any downstream bolt processing that particular tuple would essentially add its own ID and say that I'm rooted to this, I'm anchored to this particular message ID from the upstream spout. The tree is only purged when that particular tuple flows across the DAG. For example, if I have 50 different spouts, 50 different bolts in my directed acyclical graph, and I have a failure at the 46th bolt, then I would have to replay the tuple all the way from the root, which is the spout. So I will have to go back, reread that tuple, and replay it until it reaches the 46th operator. Then only can it be processed by the 47th operator. This doesn't scale out very well, especially if you have downstream failures when a particular bolt, let's say, is writing using a JDBC interface to a MySQL, and MySQL is unavailable. So now you will keep on replaying the particular tuples from all the way from the start. It's not desirable, doesn't scale well. Apex, on the other hand, uses a buffer server-based mechanism to replay all of the things, and that helps it scale horizontally. And the state of the checkpointed state of an application is purged as soon as a committed callback is received. So not much state stays is required to stay rather. Partitioning, it's standard ability to, but Storm does have the ability to set parallelism at a worker level. That's the number of containers that you have spawned across your distributed cluster, at an executor level and at a task level as well. Apex again supports parallel pipelines and unifiers and what have you. Connector library, in terms of the certified connectors, it's pretty limited. Apex has a rich set of libraries. You have good connectors robust connectors to support consumption from Kafka, Kinesis, most prominent file systems like HDFS, S3, network-mounted file systems, along with the good JDBC pollable operators, what have you. In terms of the operability, state management, you have to use external stores. Storm has introduced, guys, I'm going over time because we lost a few minutes in the initial time for operational issues. State management, external stores, you have to write to external stores. There's no native state management as such. in terms of besides the act tree. In terms of Storm has introduced checkpointing support with Storm 1.0, but it's very limited, and the user ends up writing some code for it. Checkpointing is in Storm is facilitated using a checkpointing bolt, which actually generates a call similar to the checkpoint call in Apache Apex, and then this checkpoint call flows through different spouts in Storm, and they checkpoint their own state accordingly. Right now, only a Redis-based implementation is given, so it's essentially key values checkpointing, not very rich yet, and the user has to implement a stateful bolt to achieve that. Apache Apex, on the other hand, has good checkpointing concepts. Spillover write to the local checkpoint and then asynchronously copy to HDFS. Large state can essentially be checkpointed. In terms of the recovery mechanism, the APIs to retrieve state are very cumbersome and usually end up requiring user code. For example, you want to move away from a Redis-based implementation to your own implementation or use an in-memory data grid like Geode or HDFS even. There is no implementation for that. You would have to write your own mechanism for it. Apex has incremental buffer server. So all the tuples that flow between two operators before being checkpointed are essentially written to a buffer server and replayed from that point. So that what you would get from the checkpointed state is just a count, and the tuple like we saw in the previous examples actually reside in a buffer server, and taking that count and replaying the tuple achieves you an incremental recovery. Processing semantics in Storm at least exactly once really requires a lot of user code, or you could go for an act-based one, but doesn't scale out well and is very cumbersome to do. End-to-end exactly once is supported by Apache Apex for a few input and output adapters, but between a directed acyclic graph, all the intermediate operators support end-to-end exactly once semantics. Backpressure is based on the concept of a watermark on the queue sizes for spouts and bolts. So every spout and bolt at a task level has a queue size. Every task has a bunch of tuples queued in for it to be processed. This typically doesn't scale out well because you would keep on throttling the spout until it reaches the lower watermark, and then unthrottled once you are able to consume more. Backpressure is automatic. Spillover happens to the buffer server, and from the buffer server to the disk. So buffer server is in memory, but from that in memory, spillover happens to the disk. Elasticity, yes, you can change the parallelism of some of executors in Storm using the command line interface that Storm gives you. In Apex, however, what you can do is you can actually implement a dynamic partitioner, and you can scale up and down from the user code itself. So you wouldn't need any manual intervention to do that. Dynamic topology modification, what it basically means is that today I'm consuming from Kafka, I have a CSV parser, and I'm writing and I'm flattening it and writing it to MySQL, for example. Tomorrow I may want to change that CSV parsers to write to an enricher instead, and then to a MySQL. In that case, I can actually do that. In that case, I need to introduce a new processing operator for it. Apex actually gives you to change a DAG on the fly using the command line interfaces, so that you can actually change a running application with the ability. Storm doesn't give you any of those things. In terms of security, Storm has a Kerberos support, which is native again to HDFS. But Apache Apex, besides Kerberos support, gives you a role-based access control and LDAP support coming as a part of the torrent offerings. Multi-tenancy, yes, Storm does support multi-tenancy using Mesos. It has a Yarn integration, but that project is not very active anymore, and it's pretty limited. Storm uses, again, a native scheduler called resource-aware scheduler, and the resource constraints that you can give for scheduling something using that scheduler are based on memory and CPU. Apex is Yarn native. It leverages all Yarn's APIs for scheduling and multi-tenancy. DevOps tools are pretty, they have a REST API, Storm has a REST API and a basic UI. REST APIs are usually used for interacting with a running application. Apex also has a REST API, and DataTorrent RTS gives you good tools for operational control. Here's a sample pipeline written on Apex. Here you can see data flowing in from input adapters to a parser, to an enricher, to a compute operator and a store. And the store uses a query in and a result operator. This is a drag and drop interface given as a part of the DataTorrent RTS offerings. You can essentially pull operators from your left side, click on operator, configure schemas, and write to a store. This is how the monitoring console would typically look. This is a logical plan of a DAG running. You have a file splitter which is taking one or more files as an input, splitting it into different blocks, and then a block synchronizer synchronizes them, and the file merger merges them before a tracker actually does the metadata operations for tracking. As a part of the RTS offerings, you do get real-time dashboards for visualizing what's going on in your application. These dashboards can be configured in real time as per the data that is flowing through the system. Here I've taken ad data as an example, and I'm showing average impressions, average clicks, the cost of each, etc. Few resources that can help you get started on Apache Apex. Like you can see, our footprint is growing. A couple of customer use cases. So PubMatic is one of the customers that we have. They're an ad tech company who are using Apache Apex to give revenue information. Basically, key performance indicators are showcased in real time using Apache Apex on their dashboards. Helps them take corrective actions in case one of their campaigns is not doing as well, or the revenues are falling. Again, GE is another company which is using us for their IoT applications. They're ingesting a lot of data and doing predictive analysis to reduce costly maintenance and improve customer service. We are hiring, so feel free to drop in your resumes. Appreciate you joining us. I'm just gonna hang on for a couple of minutes. Can I update an Apache Apex app and take a couple of questions? Can I update an Apache Apex application when it's running without losing state before the operator? Yes, you can actually do that. We have an interface for doing that. That's the dynamic topology change that I spoke about earlier. Guys, appreciate you joining us today. The slides will be made available on SlideShare, and the videos would be uploaded to our YouTube channels. Feel free to write in, and thank you for joining again.